A charged rod attracts small pieces of paper, even though they are electrically neutral and are insulators. To reach an understanding of this phenomenon, we'll consider the microscopic arrangement of charges in a dielectric. Many materials, even though electrically neutral, are composed of molecules that are electric dipoles. In the absence of an electric field, these dipoles are arranged randomly because of thermal movement. When an electric field is applied, the dipoles line up with it. This image exaggerates this alignment. While the bulk of the material remains electrically neutral, the application of an electric field does induce a surface charge. Even if the molecules normally are not dipolar, an electric field can induce the molecules to become dipolar. The induced dipoles disappear when the electric field is removed. The result of the existence of dipoles is that the paper acquires a surface charge in the presence of an electric field. The negative charges on the paper are attracted to the rod and the positive charges are repelled. The attractive force is larger than the repelling force because the negative charges are closer to the rod. The result is a net force on the paper that is directed toward the rod. Dielectrics, another word for insulators, are often used with capacitors. Here is a parallel plate capacitor that has been charged by a battery and disconnected from it. What happens when we insert a dielectric slab between the capacitor plates? Because of the electric field between the plates, surface charge will develop on the dielectric slab. This charge will decrease the electric field between the plates. The magnitude of the electric field between the plates in the presence of the dielectric E' is equal to the magnitude of the electric field E when the dielectric is not present, divided by a constant kappa. The value of kappa depends on the composition of the dielectric and is called the dielectric constant. The voltage across a parallel plate capacitor is equal to the product of the magnitude of the electric field and the plate separation. The voltage across the capacitor therefore also decreases by a factor of kappa. Because the voltage on the capacitor decreases while the charge remains the same, the capacitance increases. Starting from the definition of capacitance, the new capacitance can be determined as shown. The capacitance increases in proportion to the dielectric constant. The capacitance of a parallel plate capacitor is multiplied by the dielectric constant kappa. A parallel plate capacitor has square plates that measure 1 centimeter by 2 centimeters and are separated by 1 millimeter. A dielectric with a dielectric constant of 5 is inserted between the plates. Correct. Here is the solution. A dielectric slab is inserted between capacitor plates while they are connected to a battery. What will happen to the charge on the capacitor plates? Correct. The battery adds charge to the capacitor to maintain the voltage across it.